Hello. Today I'd like to answer a question from one of the viewers, and it has to do with plasma art. It's pretty cool. So the viewer asks, why do you think transient luminous events often appear as red or blue glows rather than the usual white streaks of lightning? They are so beautiful, but why are they so rare? I've never seen one before. Can plasma be used to create large public visual performances like laser? Very awesome question. And yeah, I thought about that a lot and did some work in that direction. But let's deconstruct this little Pandora's box. So first, let's talk about how this whole thing happens. Why is there light associated with plasma? So, we're on a big piece of rock flying through space, but there is space around us. So there is radiation coming from the sun, high energy photons flying in all directions, and occasionally they knock an electron out of a molecule. And now you have this free electron. Who cares, right? Well, you have lots of charges floating around, especially in open space. So occasionally there is, for one reason or another, there is a potential difference. So kind of plus here and kind of a minus here. And then you have an electron. So electron is repelled by the minus and attracted to the plus. So it starts flying around. And if that plus is big enough, electron begins to accelerate. And if it accelerates to the point where its energy is enough to knock another electron out of a molecule, well, you start transitioning to the state that we call plasma or ionized gas. So this initial seed, so-called seed electron, begins to ionize the gas around. And what does that mean? So let's say you have a molecule like nitrogen, N2, just sitting there, calmly relaxed state, and all of a sudden the electron comes, boom, yeah, boom, blah, blah, poof. So the nitrogen molecule is very excited. And eventually, that excitation is relaxed, and during the relaxation process, the molecule can emit a quantum of light. Too many details to go into why that happens and how that happens and the quantum mechanics around it. Just assume that to be the fact. Sometimes when molecules relax from higher energy states to lower energy states, they emit light. And usually the light emission is different for different molecules and just different situations. For example, typically nitrogen relaxation emits purplish, violetish, pinkish, purplish, depending on who you ask, but kind of a purple light. Oxygen, I call it white. Many people call it pale blue, whitish. Argon is lavender, blue-violet kind of range. Helium is, I'm reading it off the sheet of paper here because I'm not going to remember all of those. Helium is pink, orange, sometimes salmon, okay? Neon is bright red, orangish color. You've seen the neon signs, especially at the old bar, open and it's blinking, and we can talk about why it's blinking maybe in a different video. Hydrogen, pure hydrogen is magenta color. Xenon is blue or blue-violet type of color. Krypton is similar to oxygen, is whitish. And mercury vapor, for example, is blue. And it also emits strong in the UV range. And there are many others, and also mixtures of them. So on Earth, we have lots of nitrogen. We have lots of nitrogen, lots of oxygen. So if you ignite plasma on Earth, you have oxygen emission, which is kind of whitish. and nitrogen emission, which is kind of purplish. So you will have, as a result, white plus purple will look purple. So what if you take pure oxygen? What does it mean, pure oxygen? Oxygen and nitrogen, they have similar boiling points. They're actually kind of difficult to separate. So you can buy a tank of medical grade oxygen, which is, 349s, which is 99.9%. So let's take 99.9% oxygen. Well, there is the 0.1% impurities. That impurities are typically nitrogen, maybe a bit of water, but lots of nitrogen. So if you ignite plasma in this medical grade oxygen, you will still have emission from nitrogen. So purple will actually overtake. And if you buy medical grade oxygen tank, plasma will still be purple. So you need to go to ultra high purity oxygen tanks like 7 nines, 8 nines, so 99.99999% purity. There's still some impurities, but that plasma will look white, assuming you purged your chamber, etc., etc., etc. So it's a little challenging to get these things. The analogy I like to give to students, imagine you have a barrel of honey and you add 0.1%, just a teaspoon. You have a whole barrel of honey and you add just one small teaspoon of poop. What do you have? You have a barrel of poop now. So even small addition of impurities could alter the system quite a bit. Another question that the viewer is asking, or part of the question, is why is the lightning white? Well, lightning, first of all, it ionizes lots of different stuff. Oxygen, nitrogen, water, everything is ionized. Lightning is very high energy. There is also just broad spectrum emission of very hot plasma. So your eyes, they just integrate it as white. You're not a spectrometer. You can't see the specific spectral lines. And when you see all of them together, you interpret it as white. So lightning appears as white, and aurora borealis and these transient luminous events, they have colors. Why do they have colors? They're in upper atmosphere. Pressure is lower there. So the plasma that's ignited in that rarefied gas is able to show you colors of the specific molecules and metals and whatever else is present in the upper atmosphere. It's present at low concentration, but enough to broadly emit light. Now, if you're lucky enough to see aurora borealis or these transient luminous events, they are multicolor and really beautiful, kind of like weird paintings in the sky. And a total tangent on that. I live in Ohio now, and a friend visited, and she's like, oh my God, guys, we got to go to check out the Serpent Mound. It's maybe 3-hour drive, like southwest from here. So we got in the car, drove, and this is this ancient, some people claim that it's as old as 10,000 years. This is this kind of like a mound. And they call it the Serpent Mound because it looks like a dragon that's sleeping. But when I stood at it, and I'll try to find a picture of it, when I stood looking at it, it looks just like the Northern Lights. So you imagine thousands of years ago, you are chilling at night by the fire, grilling the thing that you killed. And all of a sudden you see these lights on top of your head in the shape of a dragon or a serpent. What do you do in response? Well, you have to talk to the gods. So you build a mound, a little mountain that resembles the shape of the plasma in the sky. It's pretty cool. When I saw it, I was like, wow, 10,000 years ago, people already worshipped plasma. So I'm in a cool company. Now, why are these things rare? They're not very rare. They are not very bright. So these northern lights, like you have to go to a place where light pollution, light pollution like the city at night glows with all the light the city is producing, all of the traffic lights and the street lights and the corporate buildings. You just can't see the sky. You can't see the stars from there. I lived downtown Philadelphia for many years, and I barely ever saw the stars. I had a nice roof deck, and I would go out at night, and I'll see, a dozen really bright stars. But the light pollution from the city consumed everything else. Now, even on the outskirts of Columbus, my sky at night is much more interesting. Now imagine if you go to the desert, and I plan to do that. I want to go to Morocco with my wife and go to the desert and just lay with my back on the sand and stare at the actual sky. Without light pollution there, you would see a lot of these events, a lot of these space plasmas. But moving on. So they're not rare. It's just as we are expanding as industrialized society, the places where you can see these events are becoming more rare and rare. And they're more and more difficult to get to. So you have to fly to the desert and take a camel ride out of the city and exert significant effort to see them. But I'll bring my camera. Anyway, so let's talk about large public visual performance displays. Lasers are cool. You have this little laser emitter, and then it emits a beam of light. That light by itself is not very visible. It needs to bounce off something. So this room right now is pretty smoke-free, rain-free, particle-free. So if I shine a beam of light, you're not going to see it. So what I need to do is what nightclubs do. I need to flood this room with smoke and then shine lasers through, and then laser beam bouncing off the micro droplets of smoke will produce the light show that all of us so much admire. And if you sync it to music, man, you got a party going. Now, can we do that with plasma? Not really. Plasma, in order to generate it, you need positive, negative electrodes. So you need two electrodes, and you need a high voltage power supply. So unlike laser that shoots the beam of light into infinity, plasma is produced between the two electrodes. So when you're thinking about designing an art piece, you need to think how those electrodes will be positioned. Now, if you make one plasma arc, okay, it's cool, but it's just one arc. So it's not really that big of a piece. Like a lot of times where you see plasmas in sci-fi movies or things like that, you will see like a gliding arc or the plasma ball, and they're usually part of something else. Like it's a big installation and there is some glowing thing in a corner, simply because big plasmas are kind of hard to make. I did try to work with one of the Philadelphia's museums to try to install plasma in their fountain. They had an algae problem in the fountain, and plasma is very good at killing algae in the water. So we could have this glowing plasma in the fountain, and the fountain would glow at night while killing algae. Well, that's all good and fun, but plasma is high voltage, water is conductive. What if something goes wrong and the kid that jumps in that fountain, they're not supposed to, but kids are kids. What if something terrible goes wrong and the grounding connection is just bad and the water gets the high voltage. And there is a kid in it. So there is a potential for accident. And finally, we decided that for safety's sake, we're not going to go with that. So unlike laser, which everything is embedded in the box, and then the beam that comes out is relatively harmless unless you stare right into it. So typically lasers, they're on top of your head. They rarely shine into your eye. So can plasma be used to create visual performance displays? Theoretically, yeah. Practically, plasma for displays has been fully replaced with LEDs, even though plasma is brighter. You know, plasma TVs, they're super bright, but they have limited lifetime because plasma burns the TV out faster. And plasma TVs are just more expensive than LEDs and OLEDs, so we end up with LED displays. Very cool, bright, nice. You can watch movies on them, but again, you know, plasma is a little too expensive and a little too damaging. And also you have those same high voltage issues, so there's safety concerns and all of that. So can plasma be used for performance art displays? It could, but it typically ends up being expensive and dangerous, so it very rarely, if ever, is, unfortunately. But hey, thank you for the question. This was a cool one to answer. Every so often, at a plasma conference, we would gather around, usually with beers, and a couple of conversations always come back, and using plasma for art displays is always present. So all of us as a community are always keeping that in the back of our heads. And if you have some cool ideas for plasma art, I would love to hear them. Along with any interesting questions that you may have, please post them down in the description. I'll be happy to make another video about them. Thank you. Peace. I'll see you in the next one.